Hi everybody, and welcome to the third and last video in my series on graphing rational functions. So, I've already started this example because I'm sure you've already watched the first two videos, which you need to understand this one, and we have a lot of work to do to finish this problem out. But, a quick recap, we found the y-intercept by plugging in x equals 0. So we evaluated the function at 0, you get negative 8 over positive 12, which is negative 2/3. Then we found the x-intercepts. Those happen when the top equals 0, as long as there's no holes. See video number 2 for that. So we have x-intercepts at negative 4 and positive 2. I graphed those. And then we have a vertical asymptote at x equals negative 3. That's when the bottom equals 0, and I graphed that as well. So you might be thinking, well, there's only one thing to do, and that is we need to find the end behavior asymptote. Now, you might remember the rule from Algebra 2 that if the degree of the numerator is more than the degree of the denominator, then there is no horizontal asymptote, and that's true. However, there still is an end behavior asymptote. So our rule is going to be this, and I'm going to abbreviate quite a lot. If the degree of the top is 1 more than the bottom, you have a slant asymptote. Now, slant here means a line. So we're going to have a line just like y equals mx plus b, that kind of line. Our asymptote, our end behavior asymptote, is going to get close to a line like that one. Now the question is, how do we find such a slant asymptote? And the good news is, we already know how to do it. We've learned the technique earlier this year, in fact. You may not be happy though. The technique that we have to use is polynomial long division. So x squared plus 2x minus 8, we divide by 4x plus 12. So let's get ready to do some long division. All right, step 1. We're going to look at the first terms of our quotient and our dividend. And I ask, what do I multiply 4x by to get x squared? Well, I'm going to have to multiply by 1/4 to make the 4 go away, and I have to multiply by x. So x times x is x squared. So we've built a part of our quotient, and then we multiply by the divisor. 1/4 times 4x is x squared. That was the whole idea. 1/4 x times 12 is 3x. Put that in parentheses, subtract. X squared minus x squared cancels, that better cancel. 2x minus 3x is negative x. Then you bring down your next term. Okay, repeat the process. Look at the first term, 4x, and now look at negative x. So what do I need to multiply 4x by to get me negative x? Well, I'm going to have to multiply by a negative. I have to multiply by a 4th to make the 4 go away, and that's it. I already have my x. So we have a new part of our quotient. Multiply by the divisor. Negative 1/4 times 4x is negative x. That was the idea. Negative 1/4 times 12 is negative 3. Put that in parentheses and subtract. First terms cancel. Negative 8 plus 3 is negative 5. That's our remainder. Now, long story short, and then I'm going to give you the reasoning behind it, our slant asymptote, our end behavior asymptote, is this quotient. That quotient is our end behavior asymptote. Now the question is why? You have to go back to what long division means. So, go back in your notes if you have them, but we have the dividend over the divisor equals the quotient I'm going to put that in parentheses just for emphasis, plus the remainder over the divisor. If this looks familiar, this is exactly how you convert to mixed numbers when you learn about mixed numbers in whatever early grade that is. But it's here. Everything is here that you need to understand. So let's look at why that might be the case. So remember, an end behavior asymptote only makes sense at the end of your x-axis. Very large positive numbers and very large negative numbers. Well, if you think about it, if x is a very large positive number, think about this guy. If x is a very large positive number, you have -5 over a really big number. So just to put this in some specific context, let's just pretend that x was 1 billion. You'd have -5 over 4,012,000,000. Okay, -5 over something in the billions, guys, that's very close to 0. -5 over 1 billion, 0.0000, a whole bunch of zeros and then a 1. So this part is basically 0, which means the function looks like that at the end, and that's exactly what an end behavior asymptote is for. All right, long story short, do the polynomial long division, your quotient is the slant asymptote. So let's graph the slant asymptote. Now, fractions, let's just do the best we can. So the y-intercept is at -1/4, and the slope is +1/4. So I'm going to count over 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. Up 1. So I'd be about there. And then 1, 2, 3, 4, up 1 again. Now, just like in the previous examples, I do not like drawing my end behavior asymptotes in the middle of the graph because they simply don't apply there. All right, let's draw the other half. So y-intercept is here. So let's count 1, 2, 3, 4, down 1. 1, 2, 3, 4, down 1. Now you can draw the asymptote all the way across the graph if you want. This is just my personal preference. Okay. Just like in the first video, we may or may not have to work on finding the limit behavior at the vertical asymptotes. If you remember, that means we need to find the limit as x approaches -3 from the left, and the limit as x approaches -3 from the right. So we might have to find these by, if you remember the first video, thinking about numbers really close to the left or right. It would be nicer, though, if we didn't have to do that. And in this example, we also don't. So let's think it through. Look at these 2 points. So our graph is going to have to connect those, right? And then could the graph turn around and go to positive infinity? And the answer is no, because I know my only x-intercepts are at -4 and +2. If the graph tried to turn around and approach positive infinity, I would get an x-intercept somewhere in that neighborhood, and I know that doesn't occur. So the graph can't go to positive infinity on that side of the axis, which means it has to go to negative infinity. And I know I have to get close to the end behavior asymptote. Let's try not to cover it up completely. Just get close to it. So that's the right side. What about the left? Well, let's use our facts about multiplicity like we did in the previous video, I think. The factor that gives us the x-intercept at -4, this one, has exponent 1. That means it's odd multiplicity. So let's look at what we know. I know the graph has to get close to this slant asymptote, and I know I have to touch at this x-intercept, and because this is odd multiplicity, I have to cross the axis. Well, that means I have to continue to positive infinity. I can't turn around and go to negative infinity for the same reason as before. I can't pick up another x-intercept because I know there are only 2. We found them. So without doing any work, we found this was positive infinity and this was negative infinity. Just remember, if there's not enough information present in the graph, let's say to find this left limit, you could pick negative 3.0001, plug that into the factors. If you did that, you would get a positive number, and then a negative number, and then another negative number. Multiply all this together, that's positive, so you get positive infinity. It checks out. So sometimes you can just do this by thinking about the graph. Sometimes it requires this little stick figures thought process. Anyway, between these 3 videos, you pretty much know how to graph any rational function that you are likely to come across. So, hope this helped.